Hey guys, this lesson is on the basics for how to construct Lewis structures for covalent compounds. So basically, Lewis structures are pretty simple models that just show the atoms that are in the compound and how the valence electrons are being used to either make bonds or be lone pairs within these models. Now, if you had a single atom all by itself, a Lewis structure would simply be the element's symbol with a number of dots around it showing the number of valence electrons. In a previous lesson, we showed you how to get that number of valence electrons just by looking at the column number. Group 1 has 1 valence electron, group 2 has 2 valence electrons. When you get over to groups 13, 14, and 15 up to group 18, you can just look at the ones place. Group 14 has 4 valence electrons, and so on and so forth. Well, so carbon's in group 14, and therefore it has 4 valence electrons, and so you could just show the symbol with 4 dots around it if you wanted to. Fluorine is in group 17, and you could show it with 7 valence electrons then. Okay? Now, in a molecule, some of the electrons are shared between atoms, and it takes 2 electrons to make a bond. Okay, that's very important. It takes 2 electrons to make a bond. Now, if you kind of looked at the noble gases, if you remember from the previous lesson, we were talking about why those gases were stable. They, except for helium, all have 8 valence electrons, and that's kind of a magic number, 8. And so most of the time, when we're talking about nonmetals bonding, they try to increase the number of valence electrons surrounding each atom to 8. And so that 8 has more stability than other numbers of electrons. Now, there's some important exceptions to that. Hydrogen is, because it only has 1 energy level, is stable with 2 electrons. And the elements that have 3 or more energy levels may actually have more than 8. I've seen this go up to 10 or to 12 for something like phosphorus or sulfur. There are a couple of extra elements that can go less than 8. For instance, beryllium can be happy with 4 electrons, and boron can be happy with 6 in certain scenarios. But most of the time, you're trying to get atoms to follow this octet rule here. Okay. So there are some basic steps in drawing a Lewis dot structure. And if you'll look on, for my students, if you look at the right side of your first assignment in Unit 2A, these steps are listed there for you. So you can refer to those as needed. But, because we're using valence electrons to make models, it's really important that the first thing that you do is add up the total number of valence electrons of all of the atoms that are inside the molecule, okay? Then you can connect the atoms together with a dash. And remember, these dashes represent bonds, and so every time you draw a dash, that's 2 electrons. Now, if you're trying to decide which atom to put in the middle, usually the atom that you only have 1 of, the unique atom, goes in the middle, or the one that has the lowest electronegativity might go in the middle. Hydrogen can never go in the middle because if it did, then it would have more than 2 electrons just by making connections to more than 1 other atom. So hydrogen will never be a central atom. Then you're going to add in some extra electrons as dots to try to complete the octet, the 8 electrons, for as many atoms as you can until you hit your total. Now, it's really important that in this step you stop at the total number of electrons that you came up with in step 1. Okay, so you can't use more valence electrons than the atoms would have together. Now, sometimes you add in all of your electrons and you don't have enough electrons to get all of the atoms to be stable, to have 8 electrons around them. And so if that's the case, then we're going to make some double or triple bonds by moving some lone pairs of electrons in to make bonds. And, there's a couple of things you probably want to do when you get to the end to check yourself, check and make sure your total electrons and your dots and your dashes add up to the total that you got number 1, and you haven't accidentally put any extra or electrons in there or taken any out. And then you also want to make sure that around every single atom in your molecule, all the atoms are stable. Okay, you followed the octet rule or possibly one of the other broken rules, but we'll get into that later. Okay, so for a molecule like CH4, if you were to add up the total valence for this, carbon would have 4 valence electrons, and hydrogen has 1 valence electron. But now there are 4 of the hydrogens, and so if you were to multiply this 1 by 4, 4 ones is 4. So basically 4 and 4 is 8 total here. Okay, and again, I'm looking at the column numbers to figure out, hey, carbon's in group 14, it's got 4 valence electrons. Hydrogen's in group 1, so it's got 1 valence electron. That's step 1, add up the total. Step 2, connect your atoms together with a single bond. Now, carbon is the unique atom here, so I'm going to put carbon in the middle and connect all of the hydrogens to the carbon in the middle. Okay, now remember, how many electrons are in a bond? 2. So every bond that I made with this carbon to each hydrogen has 2 electrons in it, and I've already got the total of 8 electrons. Now so I don't have any dots to add in that next step. This is kind of a unique case because hydrogen has a situation where it is stable with only 2 electrons, and you can see there's 2 electrons in the bond touching this hydrogen, and so it already has its 2, and that's true for all 4 hydrogens. The carbon, if you look at it, is touching 4 bonds, each having 2, so 2, 2, 2, 2, and that's a total of 8. And so this molecule is already completed and already stable that way. It's a pretty simple model. This is methane gas. All right, so now if you take a look at a molecule like carbon dioxide, this is a little bit more complicated. Simply because we've got a few more valence electrons and things don't work out quite as neatly and evenly as they did in the previous example. But let's go ahead and go through the process again. All right, so if you start adding up the total valence for this one, carbon has 6 valence electrons, and each of the oxygens, carbon has 4 valence electrons, and each of the oxygens has 6. Okay, there's 2 O's here, so 4 for the carbon and 6 and 6 make a total of 16 electrons. Now carbon again is the unique atom here, so I'm going to put carbon in the middle and connect it to a couple of oxygens. Now it's important to, when you're going through this process, to see, okay, how many electrons have I already used when you connect your atoms together out of your total. So I've already used 2 dashes, which is 4 electrons. So I've already used 4 out of this 16, and I'm only going to have, so your 16 minus 4 would be 12 left over. So I can add 12 dots in here, and I want to try to add them in a way that it's going to make as many of the atoms stable as possible. Now this oxygen is only touching 2 electrons, so it needs 6 more. So I could put 6 dots on this oxygen. The difference between a dash and dots is that the dots are showing these valence electrons are only available to this oxygen, whereas this dash is shared electrons. This is a bond where those 2 electrons are actually connected to both atoms on either side of it. Okay, so far 2, 4, 6, 8, 10. I've used 10 out of the 16. I'm going to keep going. 12, 14, and 16. Okay, all right, so I've got my 16 electrons in here. I cannot go past that because I've already hit this total. Now, this carbon isn't stable yet. If you look at the oxygens, these are all touching 8 electrons, but the carbon's only touching 4 electrons, and so it needs 4 more. I can't add more dots or else I would go past 16. The solution here is actually to move some dots. So what we're going to do is we are actually going to take some dots away from the oxygen and share them with the carbon. If we move those into there, you'll see the oxygen would still have 8, but now the carbon has 2, 4, 6 touching it. So we're sharing them to make less electrons count for more atoms. Now the carbon still only has 6 touching it in this scenario, so you might have to do the same thing on the other side. Take some electrons off of this atom and make the double bond. Now that's only necessary if you don't have enough electrons. That's the only time you're going to need to do that. All right, and I would actually prefer that you guys actually get rid of the electrons that you moved to clean up the model. Okay, so this is the final model for CO2. We've got 8 electrons touching every atom, and we've got 16 in the whole thing. Okay, so a couple of things that we need to take care of there. Okay, all right, let's take a look at PF3. All right, in this model, phosphorus has 5 valence electrons. It's in group 15, and each fluorine has 7. So 7 and 7 and 7 add up to a total of 26 electrons. Which atom are we going to put in the middle? Well, usually the atom you only have one of, the unique atom. So we're going to put the phosphorus in the middle, and I'm going to go ahead and connect that to my fluorines. How many electrons out of the 26 have I already used? There's 2 in every dash, so I've used 6. Then we want to add in dots until we get up to the total of 26. And remember, you're trying to get 8 electrons around as many atoms as you can. Okay, so I'm going to start at 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. See, I've filled up every fluorine with 8 electrons touching it. I've still got 2 left. I'm at 24, so that last pair looks like I can put them on the phosphorus here because it was only touching 6, okay? All right, so I've got 26 electrons in the whole thing, and every single atom has 8, which means that step where I move dots in to make double bonds isn't necessary here. I don't need to do that because I had enough electrons to make everything stable. Okay, a little simpler example here. We've got nitrogen. This is just N2, which means we've got 2 nitrogens that each have 5 electrons and adds up to 10 total valence electrons. Now there's no middle atom here, there's only 2 atoms, so you just start out with nitrogen connected to nitrogen, and then you can start putting in dots. Now remember, you've already got 2 here, so 2, 4, 6, 8, and then I could put 2 on the other side, 10, and I've run out. So you see one of the nitrogens was able to get enough electrons, but I didn't have enough electrons to complete the octet for the other nitrogen. So this is going to be a scenario where I'm going to have to move some dots in to make double or triple bonds. Okay, so let's go ahead and share some then. If I take this pair and move it into there, that's going to help this nitrogen out because it did have only 4 touching it. Now it's going to have 2, 4, 6 touching it. So that's better, but we're still not quite there yet. So maybe I need to take another pair and move it in and make this a triple bond. Triple bonds are as high as they go. There's no such thing as a quadruple bond. Bonds can be either single or double or triple in covalent molecules. Now, like I said, if you do have to do that, I would prefer that you clean up your molecule by getting rid of these electrons and the notation for where you moved them from and to. So we've just got nitrogen with a triple bond in the middle. And if you check here, we've got 8 electrons touching each nitrogen, 2, 4, 6, 8 touching this one and this one. And we've got 2, 4, 6, 8, 10 in the whole thing. So the total's good and both atoms are stable. All right, now sometimes you may need to do a Lewis dot structure for something called a polyatomic ion. So this thing has a charge. And this charge is not like for one of the atoms in here. This charge is for the entire structure, the entire molecule of covalently bonded atoms. And so you might remember from the last unit of study, if something is -1, that means that it has gained 1 electron. And really the only step in this process that would change is this very first step where you're adding up the total valence. Okay, so we're going to add up the total valence, and then because this whole molecule gained 1, we're going to add in 1 more. All right, so to go ahead and do this one real quick, nitrogen's got 5 and 6 and 6 and 6 for each of the 3 oxygens, plus 1, and if you add all that up, you're going to get 24. And you start building the molecule. Your nitrogen would go in the middle, connected to 3 oxygens, and when you add in your dots, you would hit your limit of 24 right about here. And you notice I don't have any more electrons. I've already hit my limit of 24, and so the solution again is going to have to be to move some in to share with the nitrogen. And it really wouldn't matter which pair that you pulled from, but you would need to erase a pair of dots from somewhere and share it with that nitrogen. It would have to be the same atom that you pulled the dots from, but here's a scenario where we have a single bond, a couple of single bonds, and a double bond. All the bonds don't have to be the same, okay? You can try this one on your own. It's a little bit more challenging. Remember, H is happy with 2, and if you add it up, 1 and 4 and 5 makes 10. This one would look like this.